class. This one starts a little bit further back. What I mean by that is it gives us the full redox equation, balanced redox equation, thankfully. And then we're supposed to separate this into oxidation reduction and cathode and anode. So here's how I would do it. Notice that one of my parts that's going to change in charge is going to be the dichromate, Cr2O7 minus 2. Notice that we have the hydrogen and the water and the chromium, and they all seem to go with the same thing. So that means I'm going to focus on this one first, and we're going to see where it plays out. Here's what I mean by that. I'm going to write down 6I minus like this, and on the other side is going to be 3I, I2 as in like iodine molecules. Notice that each one of these is 0, so there's 0 charge there, but I have 6 negative charges on the left-hand side, which means I'm going to need 6 electrons on the right-hand side to get a total of a negative 6 on both sides. Okay, that's how I find out. Once I put the 6 electrons on the right-hand side, I know this is oxidation. I know this one is happening then at the anode, because oxidation always has the electrons on the right-hand side. So I take the easiest one, the easiest half reaction I can find, one that doesn't have oxygen and hydrogen and water with it, and then I go back and I can write the other one then. And what I see is that this one here with a minus 2 means that each one of these is a plus 6, which means I have a total plus 12 here, plus the 14 pluses. Don't worry about those pluses. I have 2 Cr with a plus 6, which means with a plus 3, which means these all have a plus 6. A total of plus 6 for the chromium, and then 7 H2O, which is there purely to balance the oxygen. So that means on this side, when I have a plus 12 versus a plus 6, I need to knock down 6 of those pluses by adding 6 electrons to the left-hand side. That will give me a positive 6 here, and I have a positive 6 there, so I have the same charge on both sides, so that's good. This means it's a reduction. That means this is the cathode. So if I'm looking here, my E cell is equal to cathode minus anode, which means that if I look for iodine on table 20.1, iodine is right here. I have my plus 5,4. Let me make sure I got this right. Iodine is oxidation, which is anode, so that will be minus a plus 0.54, like that. My cathode is, there we go, is my, there he is, plus 1.33. You can see that there, it looks perfect. So this one is a plus 1.33. So I take this minus that, calculate, I really don't feel like thinking about it. So 1.33 minus 0.54 equals 0.79. So my answer then is a positive E cell like this equals plus 0.79. Notice that the balanced equations mean nothing. Those numbers in front do not change the cell potential. Does not change the cell potential. Does not factor in. Factors in for other things, but not for finding the cell potential. So let's do the next one then. Same thing here. This one's super easy because I got 3I2 like this, and now 6 iodine minus iodides are on the right-hand side. That means I definitely need 6 electrons here. That gives me a negative 6. And over here gives me a negative 6, so this right here means I have the cathode and the reduction, like that. Do the other one is 2 aluminums, goes to 2 aluminums with a plus 3. That means I need 3 electrons here. There's 2 of them, so I actually need 6 electrons here, like that. That will give me 0 charge, and over here I have 0 charge. Is that you? Okay, thank you. So that means I have anode here. We know that E cell equals cathode minus anode, just as it's written. So let's go back and check to see. Like this, the aluminum, where's the aluminum at? Is written as negative 1.66. So where's aluminum? Aluminum is the anode, so that would be minus a negative 1.66, like that. We're looking for iodine. Iodine is this one. I just saw it there, 0.54. So that makes this a positive 0.54. So we're going to add like that. 0.54 plus 1.66 equals, and our E cell for this is going to be a positive 2.20. And that's how you do it.